Right, so this video is going to be on probability charts or about, again, kind of outcome charts, however you want to call them. But we've been doing a lot of probability stuff lately, dealing just with fractions and kind of situational analysis. We're going to talk today about a method of doing these that involves kind of mapping out all the possible outcomes or all the possible outcomes that you're interested in, and using that to help guide your thinking. So the best way to talk about this is just kind of showing an example. So let's get right into it. Excuse me. So First thing here is at a certain theater, we have 30% of customers were female and 70% were male on a night where they were showing two specials, a romantic comedy and a World War II film. 75% of females and 60% of males attended the romantic comedy, and then nobody saw both films. What's the chance that if we pick somebody at random, that they saw the romantic comedy? So this is the question here. If we pick somebody at random, what's the chance that they saw the rom-com or romantic comedy? Well, again, it's best in this situation when you have a lot of stuff going on is to get your labels down. So we have basically two types of categories that people can fall in this situation, right? They can either be female or male, and they can either went to the rom-com or the war film. Now, instead of using four different variables, we can stick with just two. Female would be F, and then the complement of a female would be male, because again, there's a binary outcome here. You're either female or you're male. So you have two different situations. One is the complement of the other. So let's just do F complement, which means not female essentially, which in this case would be male, so that we can actually solve this here. And then the same thing with the rom-com. It was either there's only two films, right? The romantic comedy and the war film. So you either have the rom-com or the not rom-com, which again implies the war film. So instead of having four different variables, we're just going to have two. So if we pick a customer at random, there's four possible outcomes that can happen. We can either pick somebody who was a female and rom-com, so that'd be female and saw the romantic comedy. That's one outcome. They can either be female and they saw the war film, which would be that, so female and war film, female and rom-com, or they could be male and romantic comedy, or they could be male and war film. So those are the four possible outcomes that we can have in picking somebody. If we pick a person, they're going to fall into one of these four categories. So we're going to take these categories and make them into sort of a tree diagram following a specific outline. And the outline is this sort of setup here. And the way we made this is we basically kind of took each pair of events as it came. So if we pick somebody, the first thing we can tell is whether they're female or male. So that's our first split there. So we pick somebody. So here's some random person here. We pick that random person. They can either be female or male. And then if they're female, we have another split. They can either be female and saw the rom-com or female and saw the war film. And the same for male. Male, it could be male and rom-com or male and war film. And then at the end of this branch is this outcome. So if they're a male and they saw the war film, that means they're male and saw war film. If they're male and saw the rom-com, that means they're male and saw rom-com. And then same thing up top here. Remember this notation right here, this little line here, means, like this one right here, means saw the romantic comedy given that they're a female, which is why it's up in this upper branch here. Because if we know that they're a female, that means both of these are given that they're a female, what did they see? So think of this as the gender split and then these as the movie split. So that's kind of how we make these probability charts, is we kind of take it one set of items at a time. Now you could reverse this and do movie split first and then gender split down here. The only reason I did it this way, and the only reason we kind of follow this path here, is because we know a little bit more about the gender breakdown. 30% were female, 70% were male. So we have a little bit more information on that. So I decided to make that my first split because I want to start with information that I know right off the top. So again, usually the first split is the split you know the most about, which in this case is the gender split. Now, if I want to get, like, let's say this end probability here, if I want to get this end probability, all I need to do is multiply the two that came before it. So these two multiplied to each other gets me this. And the same thing down here. These two, whoops, sorry, a little bit off there. Try that again. I cut my little bit thing there, but that's fine. So these two multiplied together get me this probability. And then again, same goes for the ones down below here. And that's the benefit of writing it like this, is because you can actually see this rule sort of in the diagram here. That, well, yeah, if you're a female and you saw the romantic comedy, it makes sense that you're combining this probability with this probability. Because again, if you're just choosing a path here, you have to first choose this path, which means you're a female, and then you have to first choose this path, which means you saw the romantic comedy. So that's how we end up with these two probabilities to give us the and version. So how can we use this to actually solve our question here? So let's start by filling out these questions. And again, let's actually take a moment here and remember which one we're looking for. So we want the chance, what is the probability that a customer saw the romantic comedy? So we want the probability that they saw the romantic comedy. So the probability of R, which again, we don't have. We have everything that's kind of ancillary to that. We have female in R, we have female in romantic comedy, we have male in R, we have male in war film, that sort of thing. We have all these little sub probabilities, but we don't have the general, if you pick somebody, what's the chance they saw the romantic comedy? We just have the splits. So that's why, again, we're going to be using this notation so that we can combine these together to get probability of romantic comedy without any gender influence in there. So let's start by, again, breaking these down here. So we have female and male. Again, this F bar here means not female, which in this case means male. And we know from the problem, if I scoot back here a bit, that 30% were female and 70% were male. So 30% were female, so this right here is 0.3, and 70% were male, so 0.7. Let me show you I got that right. 30% female, 70% male, right? So we know those probabilities. And again, that's just from the problem, which is why I started with these two here. If you're going to do this kind of method here, you want to make sure that these first two you actually know the probabilities of, or can at least get the probabilities of, because that's going to help you later on. So let's go back up here and let's focus on this top part for a minute. The probability that they saw the romantic comedy given that they were a female. So let's read back to the problem here. We're looking for something to link up romantic comedy and females. Well, right here it says 75% of females attended the romantic comedy, which means that if we pick from the females, so given that they're female, 75% of them saw the romantic comedy, so this would be 0.75. Now, by extension, if 75% of the females saw the romantic comedy, that means over here, 25% had to see the war film because there's no other option. There's only a binary choice, either romantic comedy or war film. So again, the word problem will usually give you like half of the pair, and then you use the complement rule, so 1 minus 0.75, to get its partner pair. Even down here, 30% were female. Well, 1 minus 0.3 gives me 0.7. So each split should have this sort of complementary aspect to it, at least until you get to the ends here. So what about the male version? Well, it says here, again, 60% of males saw the romantic comedy. So given that we picked a male, the chance they saw the romantic comedy is equal to 0.6, which by the complement rule means that if 60% saw the romantic comedy, that means 40% saw the war film. Or again, the way we got this is we do 1 minus 0.6. Whoops, not 0.5, 0.6. So again, it's mainly just taking stuff from the word problem. Now, since we have these here, and I just told you that the way that we set this up, the reason we're going down this method here, is because if I want to get the ending results, I can simply multiply the two probabilities that came before it to get to the ending branch. So that means that if I take, for instance, 0.3 times 0.75, 0.3 times 0.75, I get 0.225, which is the 0.225, the end probability here. So this is the probability that I pick somebody who's a female and saw the romantic comedy. It's about 22.5%, 0.225. The chance I pick a female and that they saw the war film would be 0.3 times 0.25, which gives me 0.075. So that's the chance that they're female and saw the war film. And then for the male, again, the same idea. You just multiply the probabilities here. So 0.6, this probability, times 0.7, this probability, gives me 0.42. And then over here, we have 0.7 times 0.4. So again, 0.7 times 0.4 gives me 0.28. So this is the probability that they're a male and saw the war film, male and saw the romantic comedy. And if you notice all of these together here, if we add them all up, just to prove it, try this again, 225 plus 0.075 plus 0.42 plus 0.28 all adds up to 1, which makes sense because, again, if I pick somebody, these are the only 4 possible outcomes. So they better add up to 1 because they're all my possible situations. And again, by probability, if you add up every possible situation's probability, it should add up to 1 because one of these is going to happen. So let's try to answer the question now. We want the probability of picking somebody who saw the romantic comedy, so P of R. So you can think of this as the sum of picking a female rom-com customer or a male rom-com customer, because that's basically what the P probability of picking a romantic comedy person is, right? Those are the only 2 options for a romantic comedy result. You either pick a female that saw a romantic comedy or a male that saw a romantic comedy. Those are the only 2 possible, what we call subsets of that probability. And if I add up all the subsets of that probability, I get that probability. So the probability of picking a rom-commer would be female and rom-com and male and rom-com. So even though I can't get the major probability directly, I can get it using these little sub-probabilities, what we call subset probabilities, because again, they're a set of the entire thing here. So if this represents the probability of picking a romantic comedy person, then that means it's not exactly half, because as we see there, the chance of picking a female rom-com is a little bit less than chance of picking a male rom-com. So it might be something like this, kind of. Not exactly half, although that looks kind of half. But anyway, we have the female rom-com pickers here, so female rom-coms, and we have the male rom-coms in this section. So if I add these 2 slices together, I get the entire probability of picking somebody who saw rom-com, female or male. And luckily, our little tree chart here, our tree diagram, models that. The chance of picking a female rom-commer is 0.225, so 0.225. And for a male rom-commer, it's 0.42. So if we add these together, we get 0.645, or roughly a 64.5% chance of picking somebody who saw a romantic comedy. Which, again, you can do 1 minus this to get the chance of picking somebody who saw the war film, whether they be female or male. So again, the idea here was to, instead of trying to get at the probability directly, is to try to get at its subsets first, and then go ahead and add them together to get the entire idea. And again, this is a sum, not a product at the end result here, which is a little bit strange because usually probabilities you think of products. That's why we had to multiply these to get to this number, and we had to multiply these to get to that number. But this last one here is a sum, which again kind of switches things up a little bit. But again, if you use the union rule, you can actually see why it's an addition. So if I want the probability of picking a rom-commer, that's basically the union of female rom-commer and male rom-commer. So again, in English terms, this means the probability of picking a female rom-commer or picking a male rom-commer, or both. Well, obviously, if I pick somebody, they can't be both a female and male rom-commer. So that both part is just kind of nullified. But that's what this means in English terms, is the chance of picking a female rom-commer or male rom-commer. Well, if you remember the union rule says that if you want this probability, you take the probability of a female rom-commer plus the probability of a male rom-commer minus the probability of somebody being both a female and male rom-commer, because again, you want to avoid the double count. Well, as I just said, these are mutually exclusive events, right? If I'm a female rom-commer, I cannot also be a male rom-commer. So these 2 events are mutually exclusive, which means that this just ends up being 0, this section of it. So that means I'm left with this part right here, which is what I did up there. So that's where I get the sum from. So really, this is just a consequence of the union rule, which says that if you want the probability of 2 events in a union, which is again is the OR version, then you simply add them and subtract the probability of both of them happening, which is again a very, very early probability rule we went over. You can go ahead and look back at the probability section on the channel and kind of look at the, I think it's titled Probability of Unions and Intersections. You can take a quick review of that to know kind of where this formula comes from. So again, just a backdrop on why it's a sum, not a product like usual. So usually in probabilities, when we're combining stuff, we think multiplication. This is one of the rare cases where it's actually a sum, rather than a multiplication. So, and this idea of taking a big event and splitting it down into all its smaller events and then adding them together. That's going to come into play in the last two lessons on probability we have here before the school year closes. So um, yeah, that's all for this video. Again, pretty short one. Just going over one example of this diagram chart here. And it's one of those things here where if you practice it more, it becomes a little bit easier. So I encourage you to check it out on the homework on Alex, just so that you get some practice with it and practice labeling and all that stuff there. So especially the first split. Usually once you understand how to make your first split, which is basically the two items you know the most about, once you understand how to do this, the other ones usually fall into place. But this just takes a little bit while getting used to. So that's it for this video. Hope you enjoyed it. Hope it helped you out. Have a good day, night, or evening, or afternoon, whatever it is. And that is legit.